Welcome to Triune Biblical University Global Extension USA channel. A warm welcome to all our returning subscribers and a heartfelt greeting to our new viewers. We're so glad to have you with us today. Whether you've been following us for a while or are just joining the community, we're excited to embark on this learning journey together. At Triune Biblical University Global Extension USA, we strive to provide valuable educational content that empowers you to grow, learn, and succeed. Your continued support and participation mean the world to us. In today's session, we are diving into lecture topic, where we'll explore important concepts and provide practical knowledge that you can apply in real-world scenarios. This lecture is designed to challenge your thinking and deepen your understanding, whether you're a beginner or an advanced learner. Thank you for joining us, and we hope you find today's lecture both insightful and inspiring. Let's get started. Chapter 13. Geotechnical Modeling and Analysis. 13.1 Analytical Techniques in Geotechnical Engineering. Geotechnical engineering often involves complex systems where soil behavior and interaction with structures must be accurately understood to ensure safety, stability, and sustainability. Analytical techniques play a critical role in providing insights into soil structure behavior and facilitating the design process. This section discusses various analytical techniques used in geotechnical engineering, ranging from simple closed-form solutions to more advanced numerical modeling methods. These tools help engineers predict and analyze the behavior of soils and structures under various conditions. 3.1.1 Closed-form analytical solutions. Closed-form solutions are mathematical expressions that allow engineers to directly calculate the desired values based on known parameters, such as soil properties, loads, and boundary conditions. These solutions are generally applicable in relatively simple geotechnical problems where the assumptions of linearity and idealized behavior hold. 3.1.1.1 Terzaghis bearing capacity theory. One of the most widely used closed-form solutions, the bearing capacity theory, proposed by Terzaghi, provides a means of estimating the ultimate load a shallow foundation can support without failure. The solution involves parameters like soil cohesion, friction angle, foundation geometry, and the depth of the foundation, among others. Modifications of Terzaghi's theory are used for different types of soils and foundation shapes, strip, square, circular, etc. 3.1.1.2 Settlement analysis. Closed-form equations such as those derived from elastic theory or from the work of Terzaghi and Peck are used to estimate the settlement of shallow foundations. These solutions assume a linear elastic behavior of the soil and help calculate the immediate settlement and consolidation settlement for foundations subjected to vertical loads. 3.1.1.3 Slope stability analysis. Closed-form solutions, like the limit equilibrium method, provide a way to assess the safety factor of slopes by considering forces acting on potential failure surfaces. Classic methods such as the Bishop's method or the Jambu method rely on simplifying assumptions regarding the geometry of the failure surface and the shear strength of the soil. 3.1.2 Numerical methods in geotechnical engineering. Numerical methods are essential when dealing with more complex problems where closed-form solutions are not available. These methods can model nonlinear behavior, anisotropy, and the complex interactions between soil, water, and structures. 3.1.2.1 Finite Element Method FEM. The finite element method is a numerical technique that divides a geotechnical structure or soil mass into smaller, simpler parts, finite elements, to solve complex problems. It is particularly useful for analyzing soil structure interaction, including problems like foundation settlement, tunnel design, and slope stability under dynamic loading. FEM can model various soil behaviors, elastic, plastic, viscoelastic, allowing engineers to simulate real-world scenarios and predict failure mechanisms under diorite loading conditions. 3.1.2.2 Finite Diorite Method FDM. The finite diorite method is used to approximate the solutions to differential equations governing geotechnical systems, particularly for problems involving time-dependent changes such as consolidation and seepage. FDM is often used in the analysis of seepage through soil masses, soil consolidation over time, and thermal EX on geotechnical structures. 3.1.2.3 Boundary Element Method BM. The boundary element method is another numerical technique that simplifies the problem domain by focusing on the boundaries of the domain instead of the entire volume, and is often used in geotechnical problems involving infinite or semi-infinite domains, such as seismic wave propagation or foundation interaction with large soil masses. 3.1.2.4 Discrete Element Method DM. The discrete element method is used to simulate the behavior of granular materials, such as sands and gravels, which are highly sensitive to particle interactions. DM models soil as a collection of particles or blocks, and it can simulate soil behavior under various load conditions, such as shearing, compaction, or shear band formation. 3.1.3 Analytical models for soil behavior. The behavior of soils under stress can be complex, involving nonlinearities, time dependent EX, and strain hardening or softening. Various analytical models are used to represent these behaviors and are essential for predicting the performance of geotechnical structures. 3.1.3.1 Elastic plastic models. Elastic plastic models are commonly used in geotechnical engineering to describe soil behavior, particularly for predicting the yielding and failure of soil under high loads. One of the most popular models in this category is the Moore-Coulomb failure criterion, which is widely used for understanding soil shear strength and for analyzing foundation stability and slope failures. 13.1.3.2 Viscoelastic models. Viscoelastic models are employed to describe soil behavior that exhibits both elastic and time-dependent viscous properties. This model is particularly useful for understanding the response of soils to dynamic loading, such as during earthquakes or heavy machinery operation. 13.1.3.3 Hyperbolic models. Hyperbolic models are useful for describing the stress-strain behavior of soils, especially during large deformations. These models provide a good fit for both undrained and drained loading conditions in soils like clay and sand. 13.1.4 Soil Structure Interaction (SSI) Analysis. The interaction between soil and structure plays a vital role in the behavior of foundations. Retaining walls, tunnels, and other geotechnical structures. SSI analysis seeks to predict the EX of the interaction between the foundation and the underlying soil. 13.1.4.1 Linear SSI models. In linear soil structure interaction models, the soil is treated as a linear elastic medium, and the structure's response to seismic or static loading is computed. These models are suitable for problems where soil behavior is predominantly elastic. 13.1.4.2 Nonlinear SSI models. Nonlinear SSI models consider the complex and nonlinear behavior of both soil and structures under extreme loading conditions. These models are critical for analyzing the performance of foundations during seismic events or large static loads. 13.1.4.3 Coupled SSI models. In coupled SSI analysis, both the soil and structure are treated as interacting systems that ECT each other's behavior. This approach provides a more accurate and realistic prediction of foundation performance, especially in dynamic loading conditions. 13.1.5 Geotechnical software for analytical modeling. With the advancement of computational tools, many geotechnical engineers now rely on specialized software for modeling and analysis. These software packages integrate analytical models and numerical techniques, providing more efficient and accurate results. 13.1.5.1 Popular geotechnical software. Plaxis, a finite element software widely used for soil structure interaction, deformation analysis, and geotechnical design under static and dynamic loads. ANSYS, a general-purpose finite element analysis software used for advanced geotechnical simulations, including complex structural and soil interactions. GeoStudio, software focused on geotechnical stability and seepage analysis, including slope stability, consolidation, and groundwater flow analysis. FLAC, Fast Lagrangian Analysis of Continua, a popular software for analyzing soil Behavior in geotechnical applications, especially for problems involving large deformations and nonlinear behavior. 13.1.6 Conclusion. Analytical techniques are at the core of geotechnical engineering practice, enabling engineers to design safe and efficient structures, whether through simple closed-form solutions or complex numerical simulations. These techniques allow for the prediction and understanding of soil and structure behavior under various conditions. By applying appropriate analytical models and utilizing advanced software, geotechnical engineers can make informed decisions and optimize designs, ensuring the long-term stability and safety of geotechnical infrastructure. Chapter 13. Geotechnical Modeling and Analysis. 13.2 Finite Element and Finite Adherence Methods. Geotechnical engineering involves the analysis of complex soil structure systems, where the interactions between soils, structures, and loads must be carefully modeled. To address these challenges, advanced numerical methods such as the finite element method, FEM, and the finite adherence method, FDM, are commonly employed. These methods are crucial for simulating real-world conditions and analyzing complex behaviors, particularly when closed-form solutions are not available. This section focuses on the principles, applications, and advantages of both finite element and finite adherence methods in geotechnical engineering. 13.2.1 Finite Element Method, FEM. The finite element method, FEM, is one of the most widely used numerical techniques for solving complex geotechnical problems. The method works by breaking down a complex problem domain into smaller, simpler subdomains, elements, and solving them individually. The overall solution is obtained by assembling the individual solutions of the elements. 13.2.1.1 Basic Principles of FEM. Discretization. The first step in the FEM involves discretizing the continuum into finite elements. Each element is connected by nodes, and the behavior of the system is described by mathematical equations that relate the displacement and stress at these nodes. Shape functions. Shape functions are used to approximate the variation of displacement or stress within an element. They define the relationship between the nodal values and the values within the element. Steepness matrix. The steepness matrix is a central concept in FEM. It defines the relationship between forces and displacements at each node of the finite element mesh. For a given element, the steepness matrix is computed using the material properties, e.g., Young's modulus, and geometry. Global assembly. After computing the local steepness matrices for each element, they are assembled into a global steepness matrix for the entire system. This global system is then solved to determine the displacements and stresses throughout the structure. 13.2.1.2 Applications of FEM in Geotechnical Engineering. Soil Structure Interaction SSI FEM is particularly effective for modeling soil structure interaction problems, where the interaction between a foundation and the underlying soil needs to be analyzed. It is used to simulate the response of foundations under static and dynamic loads, such as in the analysis of buildings, bridges, and retaining walls. Shallow and deep foundations. FEM allows for the modeling of complex foundation systems, including piles, drilled shafts, and mat foundations, to evaluate settlement, stress distribution, and bearing capacity. Slope stability and landslides. FEM is employed to analyze the stability of slopes, including both natural and man-made slopes, by simulating soil behavior under various loading conditions. Seepage and groundwater flow. In the analysis of groundwater flow through soil masses, FEM is used to model complex flow paths and predict the seepage patterns, which are critical for understanding the stability of foundations, dams, and embankments. Dynamic analysis. FEM is widely used to assess the dynamic response of geotechnical structures to seismic loads. This includes the analysis of soil response to earthquakes, vibration of foundations under machine loads, and wave propagation through the soil. 13.2.1.3 Advantages of FEM in Geotechnical Engineering. Flexibility. FEM can be applied to complex geometries, boundary conditions, and loadings. It can handle both linear and nonlinear behavior and is capable of modeling various types of materials, including soils with different constitutive laws. Accuracy. By refining the mesh and improving the element types, FEM can produce highly accurate results for complex problems. The method allows for a detailed analysis of stress, strain, displacement, and other important parameters. Capability to handle nonlinear behavior. Soil behavior often exhibits nonlinearity due to factors such as large deformations, plasticity, and strain hardening or softening. FEM can model these EX accurately using appropriate material models. 13.2.2 Finite Difference Method, FDM. The finite difference method, FDM, is another numerical technique widely used in geotechnical engineering. Unlike FEM, which is based on discretizing the domain into elements, FDM discretizes the problem domain into a grid of points and approximates derivatives using finite differences. 13.2.2.1 Basic Principles of FDM. Grid discretization. The domain is discretized into a regular grid or mesh, and the governing differential equations, such as the equations of equilibrium or flow, are approximated at each point on the grid. Finite difference approximation. The method approximates the derivatives of variables, e.g., displacement, stress, or velocity using finite differences between neighboring grid points. This leads to a system of algebraic equations that can be solved to find the values of the variables at each grid point. For example, the first derivative dx du dx at a point can be approximated using a finite difference formula like u x plus delta x minus u x delta x u x plus delta x u x delta x, where delta x delta x is the distance between neighboring grid points. Time stepping for dynamic problems. For time-dependent problems, such as soil consolidation or seismic response, FDM can be used with a time-stepping approach, where the state of the system is updated at discrete time intervals. 13.2.2.2 Applications of FDM in geotechnical engineering. Soil consolidation. FDM is widely used to model the consolidation of clay soils under load, where poor water pressure dissipates over time. The method helps predict the time-dependent settlement and pore pressure distribution in soils. Seepage analysis. FDM is used for groundwater flow and seepage analysis, particularly in the study of flow through porous media and determining the hydraulic conductivity and permeability of soils. Dynamic analysis. Similar to FEM, FDM is used to study the dynamic response of soils to seismic or cyclic loads. It can model wave propagation, vibration, and soil structure interaction under dynamic conditions. Heat and mass transfer. FDM is used to analyze heat and mass transfer in soils, such as in the study of frost heave or the EX of geothermal energy extraction on underground soils. 13.2.2.3 Advantages of FDM in geotechnical engineering. Simplicity. FDM is conceptually simpler than FEM and is relatively easy to implement, particularly for problems involving simple geometries or uniform grids. Efficiency. For problems with a regular, structured grid, FDM is often computationally more efficient than FEM, especially when modeling large domains or when dealing with time-dependent processes. Well suited for problems involving differential equations, FDM is particularly well suited for solving problems governed by partial differential equations, such as consolidation, heat flow, and seepage, where the solution is based on time and space derivatives. 13.2.3 Comparison of FEM and FDM. Aspect Finite Element Method, FEM, Finite Difference Method, FDM. Domain. Discretization. Divides the domain into elements with nodes. Divides the domain into a regular grid of points. Complexity. More complex, can handle irregular geometries. Simpler to implement for regular grids. Flexibility. Highly flexible, handles complex boundary conditions, and nonlinear behavior. Suitable for simpler problems with structured grids. Applications: soil structure interaction, foundation design dynamic analysis, consolidation seepage, heat and mass transfer, simple dynamic problems, computational efficiency, more computationally demanding, especially for large scale problems, more efficient for problems with regular grids and simple geometries. Accuracy: high accuracy, especially for nonlinear and complex problems. Accurate for problems involving differential equations, but less flexible in handling complex geometries. 1.3.2.4 Conclusion: both finite element method (FEM) and finite difference method (FDM) are powerful tools in geotechnical engineering, each with its advantages and suitable applications. FEM is widely used for its flexibility and ability to handle complex geometries and nonlinear behavior, while FDM is often preferred for simpler, grid-based problems or when computational efficiency is critical. Understanding the strengths and limitations of both methods allows geotechnical engineers to choose the most appropriate technique for specific problems, whether it's foundation design, slope stability, seismic analysis, or seepage modeling. Chapter 13: Geotechnical Modeling and Analysis. 13.3 Soil Structure Interaction Models. Soil structure interaction (SSI) refers to the study of how structures interact with the underlying soil or foundation. It is a critical aspect of geotechnical engineering as the response of soil and structure is interdependent. The behavior of a structure can significantly affect the stress distribution and movement within the soil, while the soil's properties influence the performance of the structure. Accurate modeling of this interaction is essential in designing foundations, underground structures, and other geotechnical systems. This section discusses the fundamentals of soil structure interaction models, including different approaches, key considerations, and applications in geotechnical engineering. 1.3.3.1 Basic Principles of Soil Structure Interaction. The concept of SSI is based on the mutual influence between a structure and the underlying soil. This interaction can be viewed as a two-way coupling where the structure affects the soil by applying loads, e.g., weight, seismic forces, and inducing deformations. The soil affects the structure by providing resistance, distributing stresses, and influencing settlement and stability. Key parameters in SSI models. 1. Soil stiffness. This defines the soil's resistance to deformation under applied loads. It can be represented by parameters like the modulus of elasticity, shear modulus, and Poisson's ratio. 2. Foundation compliance. The flexibility of the foundation or base of the structure, which can be modeled as a spring with specific steepness in different directions. 3. Load distribution. The way forces are transferred from the structure to the soil, which is influenced by the shape and type of the foundation. 4. Soil settlement. The deformation of the soil due to applied loads, which affects the overall stability of the structure. 5. Dynamic interaction. In the case of seismic loads, the dynamic response of both the soil and structure is crucial. This includes the propagation of seismic waves through the soil and the resulting vibrations in the structure. 3.3.2 Types of soil structure interaction models. There are various approaches to modeling soil structure interaction depending on the complexity of the problem, the type of structure, and the desired level of accuracy. 3.3.2.1 Simplified or Winkler Model, Spring Model. The Winkler model is one of the simplest ways to model soil structure interaction. In this approach, the foundation soil is represented as a series of independent springs, each spring representing the soil steepness at a point. This model assumes that the displacement of the structure causes an elastic reaction from the soil at each point of contact. Advantages: simple and computationally efficient. Limitations: it assumes that soil behavior is independent at each point, which is unrealistic for complex structures. The model doesn't account for the interaction between adjacent springs, which can lead to inaccurate predictions for larger, more complex foundations. 3.3.2.2 Beam on elastic foundation, Boussin's model. This model is an extension of the Winkler model, where the soil beneath a structure is treated as a continuous elastic medium. In this approach, the structure, typically a beam or slab, is modeled as a beam, and the foundation's behavior is characterized by the distribution of steepness along the beam. This approach is particularly useful for foundations with continuous load distribution. Advantages: can handle more realistic load distributions than the Winkler model. Limitations: still assumes linear elastic behavior of both the soil and the structure, which may not be suitable for large deformations or highly nonlinear conditions. 3.3.2.3 Finite Element Model, FEM. A more advanced and accurate way to model soil structure interaction is by using the finite element method, FEM, which discretizes both the soil and the structure into smaller elements and solves the coupled equations of motion for the system. This model can handle nonlinear material behavior, complex geometries, and large deformations, providing detailed results for both the soil and the structure. Advantages: highly accurate, capable of modeling complex geometries, nonlinearities, and dynamic interactions. Limitations: computationally intensive, requiring significant computational resources and time. 13.3.2.4 Boundary Element Method (BM). The boundary element method (BM) is a specialized numerical technique used for solving problems with infinite or semi-infinite domains, such as problems involving soil structure interaction. In this method, only the boundaries of the system, the surface of the soil, and the interface with the structure are discretized, which makes it computationally more efficient than the finite element method for certain problems. Advantages: effective for infinite or semi-infinite domains like large soil masses. Reduces the dimensionality of the problem by focusing on the boundaries. Limitations: can be more challenging to implement and requires specialized knowledge. 13.3.3 Dynamic soil structure interaction. When a structure is subjected to dynamic loads, such as earthquakes, wind, or machine vibrations, dynamic soil structure interaction (DSSI) becomes critical. In DSSI, the dynamic behavior of both the soil and structure is modeled to account for the interaction between them during transient loading conditions. 13.3.3.1 Seismic soil structure interaction. In seismic loading, the soil's ability to absorb and transmit seismic waves plays a crucial role in determining the structural response. The dynamic interaction between the structure and the soil can influence the overall seismic response, including effects like resonance, soil liquefaction, and foundation amplification. Key considerations: soil damping and hysteresis effects. Nonlinear soil behavior at large strains. Soil profile variations and their influence on wave propagation. 13.3.3.2 Vibration of structures. The dynamic interaction between soil and structure can also influence the vibration characteristics of the structure. This is important for machine foundations, bridges, and tall buildings where vibrations can cause excessive deflections or even structural damage. 13.3.4 Applications of soil structure interaction models. Soil structure interaction models are essential for the design and analysis of various geotechnical systems, including 1. Building foundations. Understanding how a building interacts with the underlying soil to predict settlement, differential movement, and stress distribution. 2. Bridges and overpasses. Modeling the interaction between soil and bridge foundations to prevent excessive settlement and ensure long-term stability. 3. Retaining walls. Evaluating the impact of earth pressure on retaining walls and ensuring the wall stability and performance under various loading conditions. 4. Seismic engineering. Ensuring that foundations and superstructures perform well during earthquakes by accounting for both soil and structural behaviors under seismic loading. 13.3.5 Challenges and limitations of soil structure interaction models. While soil structure interaction models are powerful tools, they come with some inherent challenges. Nonlinear soil behavior. Soil exhibits complex, nonlinear behavior, particularly at large strains, and accurately capturing this behavior requires sophisticated models, which can be computationally expensive. Soil heterogeneity. Real-world soils are not homogeneous, and the variability in soil properties, e.g., steepness, density, across the site can affect the results. Modeling complexity. High-fidelity models, such as those based on FEM or BM, require detailed input data and considerable computational resources, which may not always be practical for large-scale projects. Uncertainty in input parameters. Many soil parameters, such as shear modulus, damping ratio, and soil steepness, can be difficult to measure accurately, and their variability introduces uncertainty into the results. 3.3.6 Conclusion. Soil structure interaction is a fundamental aspect of geotechnical engineering that must be carefully considered in the design of foundations, bridges, dams, and other structures. The choice of an appropriate soil structure interaction model depends on the complexity of the problem, the available data, and the required level of accuracy. Simplified models, e.g., Winkler or beam models, are useful for initial designs or when computational resources are limited. Advanced models, e.g., FEM or BM, are necessary for more complex or critical systems, where the interaction between the structure and the soil significantly affects the performance and safety of the system. By understanding the principles, types, and applications of soil structure interaction models, engineers can make more informed decisions to ensure the safety and longevity of geotechnical systems. Chapter 13. Geotechnical Modeling and Analysis. 13.4 Geotechnical Software for Advanced Analysis. Geotechnical engineering has evolved significantly over the past few decades, largely due to advancements in computational tools and software. These tools allow engineers to conduct highly accurate analyses of complex geotechnical systems, facilitating the design and optimization of foundations, slope stability, soil structure interactions, and more. Geotechnical software packages enable the use of advanced modeling techniques such as finite element analysis, FEA, finite difference methods, and other numerical approaches that are crucial for simulating soil behavior under various loading conditions. This section will provide an overview of some of the most widely used geotechnical software tools for advanced analysis, their capabilities, and their application in solving complex geotechnical problems. 3.4.1 Key features of geotechnical software. The primary features and capabilities that make geotechnical software indispensable include advanced numerical methods. most modern geotechnical software packages use. Advanced numerical methods like finite element method, FEM, finite difference method, FDM, boundary element method, BM, and discrete element methods, DM, to simulate soil structure interaction, stress-strain behavior, and other complex phenomena. Nonlinear analysis. The software often supports nonlinear material models for both soils and structures, which is crucial for simulating large deformations, plasticity, and other real-world soil behaviors. Dynamic and seismic analysis. Many geotechnical software packages allow for dynamic analysis, which is particularly useful for simulating the effects of seismic activity, ground vibrations, and other time-dependent loads. Soil structure interaction. SSI Advanced Geotechnical Software includes specialized tools for analyzing the interaction between structures and their underlying soil or foundation, including dynamic and static EX. Geotechnical data integration. Software tools integrate geotechnical site investigation data such as borehole logs, soil properties, and laboratory test results for more accurate modeling. 3.4.2 Common geotechnical software packages. 1. Plaxis. Plaxis is one of the most widely used geotechnical software programs, specifically designed for finite element analysis, FEA, of soil structure interaction problems. It is used for a variety of geotechnical applications including foundations, slope stability, tunneling, and underground construction. Key features: 2D and 3D finite element modeling capabilities. Supports advanced soil models such as Moore-Coulomb, hardening soil, and soft soil creep. Dynamic analysis for earthquake-induced loading and soil liquefaction. Integration of data from geotechnical investigations and laboratory tests. Visualization tools for easy interpretation of results. Applications. Foundation design and analysis. Tunnel and excavation analysis. Slope stability and landslide prediction. Earthquake engineering and liquefaction analysis. 2. GeoStudio. GeoStudio is a comprehensive suite of geotechnical software tools designed for analyzing soil structure interaction, slope stability, seepage, and stress analysis. It is primarily used for 2D modeling but airs powerful analysis for a variety of geotechnical problems. Key features: modules for slope stability, slope/W, seepage analysis, seep/W, and stress/strain analysis, sigma/W. Ability to analyze soil settlement, bearing capacity, and pore water pressure changes. Advanced modeling of consolidation and consolidation-induced settlement. Numerical and graphical outputs for better data interpretation. Applications. O. Landslide and slope stability analysis. O. Design of earth dams, embankments, and retaining walls. O. Subsurface water flow and groundwater modeling. O. Foundation settlement and bearing capacity analysis. 3. FLAC, Fast Lagrangian analysis of continua. FLAC is a powerful numerical modeling software that is used for geotechnical engineering analysis with a focus on dynamic problems. It uses the finite difference method, FDM, to analyze soil structure interaction, stability analysis, and deformation problems. Key features. O supports both 2D and 3D modeling of geotechnical structures. O capabilities for both static and dynamic analysis. O nonlinear material models, including soil plasticity and time-dependent soil behavior. O useful for modeling complex loading conditions such as seismic, static, and cyclic loading. Applications. O soil structure interaction, SSI analysis. O tunneling and excavation modeling. O foundation design, particularly under dynamic loads. O slope stability analysis and geotechnical earthquake engineering. 4. Midas GTS NX. Midas GTS NX is a comprehensive geotechnical software tool that provides powerful modeling capabilities for advanced soil structure interaction problems. It is particularly effective for large-scale projects requiring complex simulations of soil behavior, including dynamic, nonlinear, and time-dependent soil structure interaction. Key features. O advanced finite element analysis, FEM, for geotechnical problems. O integrated dynamic analysis tools for seismic studies. O extensive material models to simulate different soil types and conditions. O extensive database of soil properties and material parameters for calibration. Applications. O foundation design and analysis under dynamic conditions. O soil structure interaction problems, including pile design. O slope stability, tunneling, and excavation analysis. O seismic hazard and ground motion analysis. 5. Abacus. Abacus is a general-purpose finite element analysis software package used in many engineering disciplines, including geotechnical engineering. It is known for its ability to model complex, nonlinear material behavior and large-scale simulations. Key features. O advanced finite element analysis for static, dynamic, and thermal problems. O supports large deformation and nonlinear soil behavior, including soil plasticity and viscoelasticity. O integration with dynamic analysis for seismic or vibration-based studies. O user-friendly interface with high-quality post-processing tools. Applications. O soil structure interaction SSI. O foundation design and analysis. O tunnel, dam, and embankment modeling. O seismic analysis and dynamic response analysis. 13.4.3 Choosing the right geotechnical software. Selecting the appropriate software depends on several factors, including complexity of the problem. Simple problems such as static loading of a shallow foundation may be solved with simpler software, while more complex problems, e.g., large-scale dynamic analysis or 3D soil structure interaction, require more advanced tools like FLC or Abacus. Accuracy requirements. For high-accuracy models that require nonlinear time-dependent analysis, software like Plaxis or GeoStudio is ideal. Project size and scope. Large-scale projects, such as those involving tunnels, embankments, or deep foundations, may require more comprehensive software. Packages such as Midas GTS NX or FLC. User experience. Some software packages, like GeoStudio, are more user-friendly for basic geotechnical tasks, while others, such as Abacus, require more advanced knowledge of computational modeling. 13.4.4 Benefits and challenges of geotechnical software. Benefits. Increased accuracy. Geotechnical software allows engineers to model complex behaviors accurately, improving the reliability of the design and analysis. Time efficiency. The ability to run simulations and analyses quickly saves time compared to traditional methods. Cost-effective. By identifying potential issues early in the design process, software can reduce the cost of rework and improve project efficiency. Better decision-making. Visualization tools and detailed reports assist in making informed decisions and communicate results effectively with stakeholders. Challenges. Steep learning curve. Advanced geotechnical software often requires extensive training and experience to use effectively. High computational demands. Complex models with large datasets may require significant computational resources, making it difficult to run simulations on less powerful computers. Data dependency. The accuracy of the results depends heavily on the quality and completeness of the input data, which may not always be readily available. 13.4.5 Conclusion. Geotechnical software plays an essential role in modern geotechnical engineering, enabling engineers to perform advanced analysis of complex problems with greater accuracy and efficiency. By choosing the right software tool for the specific application, engineers can optimize the design process, ensure safety, and reduce costs in their projects. The availability of specialized software packages for tasks such as soil structure, interaction, dynamic analysis, seismic analysis, and soil stabilization ensures that geotechnical professionals are equipped with the tools necessary to meet the challenges of contemporary geotechnical engineering. However, engineers must remain cautious of the inherent limitations and uncertainties of computational models and always strive to Supplement software results with thorough field and laboratory investigations. Chapter 13: Geotechnical Modeling and Analysis. 13.5 Challenges in Geotechnical Modeling. Geotechnical modeling is a critical component of modern geotechnical engineering, allowing professionals to simulate soil behavior, predict foundation performance, and design structures with greater precision. However, despite the advantages, there are several challenges that engineers face when using computational models to analyze geotechnical systems. These challenges stem from the inherent complexities of soil behavior, the limitations of modeling techniques, and the variability of subsurface conditions. This section highlights some of the key challenges in geotechnical modeling and discusses approaches to mitigate these issues. 13.5.1 Complex and Nonlinear Soil Behavior. Soils exhibit complex and nonlinear behavior under various loading conditions, making accurate modeling difficult. Factors such as plasticity, hysteresis, and strain rate dependence can significantly ECT the way soil responds to stress and deformation. Nonlinear stress-strain behavior. Soil is typically modeled using nonlinear constitutive models, which must accurately capture its stress-strain behavior under direct loading conditions. For instance, the behavior of granular soils during compaction or loading is highly nonlinear, and understanding how soil responds to both small and large deformations is crucial. Challenges. It is difficult to develop models that precisely represent the highly variable and nonlinear properties of soils, especially when dealing with complex stress states, dynamic loading, or high strains. Mitigation. Using more advanced constitutive models, such as elastoplastic models, e.g., hardening soil model, Moore-Coulomb model, and viscoplastic models, can help improve the accuracy of soil behavior predictions. Calibrating. Models with detailed experimental data from laboratory tests and field investigations also enhances model reliability. 13.5.2 Soil Structure Interaction, SSI. Soil structure interaction, SSI, refers to the mutual interaction between a structure and the underlying soil. In real-world scenarios, the response of the soil affects the performance of the structure, and vice versa. Accurate modeling of SSI is essential for the design of foundations, retaining walls, tunnels, and other geotechnical structures. Challenges. The complexity of modeling the interaction between the soil and structure, particularly under dynamic loading, e.g., seismic events, remains a significant challenge. The varying properties of soil and the geometry of structures make the problem more intricate, and assumptions made in simpler models may not always capture the full behavior of the system. Mitigation. Advanced numerical methods, such as finite element analysis, FEA, or Finite difference methods, FDM, allow for a more accurate representation of soil structure interaction, calibration of models with field measurements, and dynamic tests helps enhance model predictions. 13.5.3 Heterogeneous and anisotropic soil properties. Soil is not homogeneous. It is highly variable in both space and time. The physical properties of soil, such as density, steepness, and permeability, can vary significantly across a site, and this variability can be difficult to model. Challenges: variations in soil properties, e.g., due to stratification or the presence of heterogeneities such as boulders or voids, make it difficult to establish a representative model. Anisotropy, directional dependency of properties, also complicates the situation, as soil properties may differ in the horizontal and vertical directions. Mitigation: incorporating site-specific data from geotechnical investigations, borehole data, field tests, laboratory tests, and employing stochastic modeling techniques can help represent soil heterogeneity more effectively. In some cases, using random field theory and Monte Carlo simulations can help account for soil variability and improve model predictions. 13.5.4 Uncertainty in input parameters. Geotechnical modeling is heavily dependent on accurate input parameters, such as soil properties, e.g., shear strength, modulus of elasticity, permeability, which are often obtained through laboratory testing and site investigation. However, these parameters are subject to significant uncertainty due to inherent variability in soil properties, limitations of testing methods, and the quality of available data. Challenges: the uncertainty in input parameters can lead to highly variable results, making it difficult to confidently predict the behavior of a geotechnical system. Inaccurate or incomplete data can also undermine the reliability of the model, especially when extrapolating results to larger or more complex sites. Mitigation: to address uncertainty, geotechnical engineers often use probabilistic analysis or sensitivity analysis to assess how changes in input parameters of ECT. Model predictions: incorporating reliability-based design methods and using data-driven approaches, such as machine learning or Bayesian updating, can help reduce uncertainty and improve model predictions. 13.5.5 Dynamic loading and seismic analysis. Dynamic loading, particularly from seismic events, poses another major challenge in geotechnical modeling. Predicting the response of soil structure systems under earthquake loading is critical for the design of earthquake-resistant structures and foundations. Challenges: modeling dynamic loading accurately is complex due to the need to simulate time-varying loads and soil behavior during seismic events. Additionally, soil nonlinearity and potential phenomena such as sol liquefaction or settlement. Under-cyclic loading add to the complexity. Mitigation. Advanced dynamic analysis techniques, including time history analysis, response spectrum analysis, and liquefaction models, are essential for seismic design, incorporating site-specific seismic hazard assessments and using nonlinear dynamic models can improve the accuracy of earthquake-induced behavior predictions. 3.5.6 Computational resource limitations. Geotechnical modeling, especially for large-scale or highly complex systems, can be computationally intensive. Models involving 3D simulations, dynamic analysis, or non-linear material behavior often require substantial computing power, which may not always be readily available. Challenges. Complex models may take a long time to solve, especially when large datasets or detailed mesh refinements are required. High computational demands may limit the ability to explore different scenarios or conduct parametric studies in a reasonable time frame. Mitigation. Optimizing the mesh size, simplifying the model where possible, and using parallel computing or cloud-based solutions can help alleviate computational limitations. Moreover, advances in machine learning and surrogate modeling may offer alternative approaches to reduce the computational cost of certain geotechnical analysis. 3.5.7 Validation and calibration of models. Once a geotechnical model has been constructed, it must be validated against real-world data to ensure its accuracy. This involves comparing model predictions with field observations, such as settlement, pore water pressure, or soil displacement. Challenges. Validation and calibration are often limited by the availability of accurate field data, and there may be discrepancies between the model's predicted results and actual field measurements due to the complexity of the subsurface environment. Mitigation. Using a site-specific calibration process is essential for improving model accuracy. Engineers should also employ back analysis techniques, where model parameters are adjusted based on observed field performance to improve predictions. Incorporating real-time monitoring data into the model during construction or operation can further refine the model. 3.5.8 Conclusion. Geotechnical modeling provides powerful tools for analyzing complex soil structure systems, but it is not without its challenges. Addressing issues such as nonlinear soil behavior, soil structure interaction, data uncertainty, and computational limitations requires a combination of advanced techniques, careful model calibration, and the integration of site-specific data. By acknowledging these challenges and employing best practices, engineers can significantly improve the reliability and accuracy of their geotechnical models, ultimately leading to safer, more efficient designs. Continued advancements in computational methods, hardware, and software will help mitigate many of these challenges, making geotechnical modeling an even more essential tool in future engineering projects. Chapter 14: Geotechnical Engineering for Infrastructure Projects. 14.1 Geotechnical Design for Roads, Bridges, and Tunnels. Geotechnical engineering plays a critical role in the design, construction, and maintenance of infrastructure projects, particularly roads, bridges, and tunnels. The interaction between the soil and the structure is essential for ensuring the safety, performance, and longevity of these projects. This section explores the importance of geotechnical design in infrastructure development and highlights the challenges and considerations engineers must address when working on these types of projects. 4.1.1 Geotechnical Considerations for Roads. Road design is influenced by various geotechnical factors, such as soil properties, subgrade strength, drainage conditions, and environmental factors. A thorough geotechnical investigation is required to determine the suitability of the foundation, materials, and design appropriate pavement structures. Subgrade evaluation. One of the primary geotechnical considerations in road construction is the evaluation of the subgrade soil. The subgrade must have adequate strength and low compressibility to prevent excessive settlement and deformation under icy loads. Engineers assess the subgrade soil through laboratory tests, field tests, e.g., standard penetration tests, and site-specific investigations to determine its shear strength, compaction characteristics, and load-bearing capacity. Pavement structure design. Based on the subgrade's properties, the pavement structure is designed to provide sufficient strength and durability. This involves selecting appropriate materials for the base, subbase, and surface layers, as well as determining their thicknesses. The use of geosynthetics in road construction can also improve the overall performance of the pavement by reinforcing the subgrade and reducing settlement. Drainage. Proper drainage is crucial to the long-term performance of roads. Poor drainage can lead to erosion, weakening of the soil, and water-related distress in pavement structures. Geotechnical engineers design drainage systems to manage water flow, prevent soil erosion, and maintain the stability of the roadbed. 4.1.2 Geotechnical Considerations for Bridges. Bridges are complex structures that require careful geotechnical design to ensure their stability and safety. The foundation design, typically involving deep foundations such as piles or drilled shafts, depends on soil conditions, load distribution, and environmental factors. Foundation design. The choice between shallow or deep foundations depends on the soil properties and depth of competent bedrock. Pile foundations are often used for bridges over water bodies or in areas with deep soft soils, whereas spread footings or drilled shafts may be suitable in areas with competent bearing strata near the surface. Soil structure interaction. SSI geotechnical engineers must evaluate the soil structure interaction to ensure that the bridge's foundations respond appropriately to applied loads and settlement. The interaction between the bridge piles and the surrounding soil x the distribution of stresses in the foundation and the overall performance of the bridge. Seismic considerations. In areas prone to seismic activity, the geotechnical design must account for potential ground shaking, soil liquefaction, and other earthquake-induced EX. Engineers use dynamic soil structure interaction analyses to assess the bridge's response to seismic events and ensure that the structure can withstand the forces generated during an earthquake. Foundation settlement. Differential settlement between bridge piers or foundations can lead to structural damage. Geotechnical engineers design foundations to minimize settlement and ensure that the bridge remains level over time. This may involve ground improvement techniques, such as soil stabilization or deep soil mixing, to enhance the foundation's performance. 14.1.3 Geotechnical considerations for tunnels. Tunnel construction presents unique geotechnical challenges, particularly due to the variability of subsurface conditions, groundwater, and the potential for ground movement. The design of tunnels requires a detailed understanding of the soil and rock conditions, groundwater flow, and the potential for tunnel collapse or deformation during excavation. Geological and geotechnical surveys. A comprehensive geological and geotechnical survey is essential for identifying subsurface conditions and determining the type of tunnel support system required. For tunnels in rock, engineers must assess rock mass properties, including strength, jointing, and permeability, to select appropriate tunnel boring machines, TBMs, or drilling methods. Tunnel lining design. Tunnel linings are designed to support the tunnel structure and prevent collapse during excavation. The lining must be designed to withstand the stresses generated by the surrounding soil and rock, groundwater pressure, and potential seismic forces. Common tunnel lining materials include concrete, steel, and shotcrete. Groundwater control. In many tunnel projects, groundwater can pose significant challenges. Groundwater ingress can increase excavation difficulty, cause erosion, and weaken the surrounding soil or rock. Geotechnical engineers assess the groundwater conditions and design appropriate methods for controlling water inflow, such as installing dewatering systems or using grouting to seal the tunnel walls. Ground movement and settlement. Tunneling operations can lead to ground movement and settlement above and around the tunnel, potentially affecting nearby structures. Geotechnical engineers conduct ground movement analysis to predict and mitigate settlement, displacement, and the risk of surface subsidence. Ground reinforcement techniques, such as soil nails or jet grouting, may be used to stabilize the ground during tunneling. TBM and excavation method selection. For tunnels, selecting the right excavation method, such as tunnel boring machines, TBMs, or cut and cover techniques, is crucial. Geotechnical engineers assess soil and rock conditions to determine the most efficient and safe method of excavation, ensuring minimal disturbance to surrounding areas. 14.1.4 Challenges in geotechnical design for infrastructure projects. Geotechnical design for infrastructure projects such as roads, bridges, and tunnels present several challenges. Uncertainty in subsurface conditions. Subsurface variability often leads to uncertainty in the design process. Geotechnical engineers must account for soil variability and adjust designs based on a combination of field data, laboratory testing, and experience. Stochastic modeling and probabilistic design can help quantify this uncertainty and guide design decisions. Site accessibility. In remote or urban locations, site accessibility may limit the type of geotechnical investigations and data collection that can be performed. Engineers must adapt their methods to overcome logistical constraints and ensure that accurate data is gathered for design. Environmental and sustainability considerations. Infrastructure projects must consider environmental impacts, including soil erosion, habitat destruction, and water quality. Geotechnical engineers must incorporate sustainable practices, such as using eco-friendly materials, reducing the carbon footprint, and ensuring minimal environmental disruption during construction. Seismic and dynamic loading. For infrastructure projects located in earthquake-prone regions, engineers must ensure that designs can withstand seismic forces. This requires advanced dynamic analysis, soil structure interaction modeling, and the application of earthquake-resistant design techniques. 4.1.5 Conclusion. Geotechnical design for roads, bridges, and tunnels is fundamental to the success of infrastructure projects. Engineers must consider a wide range of geotechnical factors, including soil properties, foundation design, soil structure interaction, and environmental considerations. Through careful site investigation, advanced modeling and design optimization, geotechnical engineers can ensure the safety, stability, and longevity of infrastructure projects, ultimately contributing to the development of resilient and sustainable infrastructure systems. Chapter 14. Geotechnical Engineering for Infrastructure Projects. 14.2 Airport Runways and Terminals. Geotechnical engineering plays a crucial role in the design, construction, and maintenance of airport runways and terminals. The performance of airport infrastructure depends significantly on the understanding of soil conditions, foundation design, drainage systems, and environmental considerations. This section explores the essential geotechnical aspects involved in the construction and maintenance of runways and terminal buildings, with an emphasis on soil behavior, load-bearing capacity, and long-term performance under dynamic loading conditions. 4.2.1 Geotechnical Considerations for Airport Runways. The design of airport runways involves complex geotechnical analysis to ensure that the soil and foundation structure can withstand the heavy loads associated with aircraft take-off and landings. The primary geotechnical considerations for airport runways include subgrade strength and soil composition. The subgrade under the runway must provide sufficient strength to bear the repetitive and high-impact loads exerted by aircraft. Engineers assess the soil's bearing capacity through a variety of tests, including California Bearing Ratio, CBR, plate load tests, and standard penetration tests, SPT. The soil should have low compressibility and high shear strength to avoid excessive settlement and deformation. Pavement design and layering. Runway pavements are typically designed in multiple layers, including surface layers, base layers, and subbase layers, with each layer serving a specific function to distribute the loads. The surface layer often consists of asphalt or concrete, while the base and subbase layers are typically made from granular materials. The thickness and composition of these layers depend on the soil conditions, icy loads, and environmental factors. Soil compaction and stabilization. The subgrade and pavement layers need to be adequately compacted to ensure that they provide sufficient load-bearing capacity and prevent future settlements. Geotechnical engineers use compaction tests, such as the Proctor compaction test, to determine the optimal moisture content and compaction work for the soil. In cases of weak or compressible soils, stabilization techniques, such as the use of geosynthetics or lime stabilization, may be employed to enhance soil strength and reduce settlement. Drainage systems. Adequate drainage is vital for the long-term performance of runways. Water accumulation in the subgrade can lead to soil weakening, frost, heave, and pavement distress. Engineers design drainage systems that include surface drainage, e.g., slopes, channels, and subsurface drainage, e.g., French drains, perforated pipes, to manage water and prevent soil erosion or moisture-related problems. Geosynthetics for pavement performance. The use of geotextiles and geogrids in runway construction can improve the overall performance by reinforcing the soil, reducing rutting, and distributing loads more evenly across the subgrade. Geosynthetics are particularly beneficial in areas with weak or high moisture soils. 4.2.2 Geotechnical considerations for airport terminals. While the primary geotechnical focus for airport terminals lies in the foundation design and soil conditions beneath the terminal building, the considerations are similar to those of large, complex structures. Some key aspects include soil investigation and foundation design. The terminal building's foundation design must accommodate heavy icy loads, structural weight, and the dynamic forces resulting from daily operations. A thorough subsurface investigation, which may include boreholes, geophysical surveys, and laboratory tests, helps determine the soil shear strength, settlement characteristics, and groundwater conditions. Based on these findings, engineers decide whether to use shallow foundations, such as spread footings, or deep foundations, such as piles or drilled shafts. Foundation settlement and differential movement. Due to the size and complexity of airport terminals, foundation settlement and differential movement can have significant impacts on the structure. Engineers must design the foundation to limit both total and differential settlement, which could result in cracks or misalignment. Ground improvement techniques, such as vibrocompaction or soil grouting, may be used to improve weak soils and reduce settlement. Earthquake resilience and seismic design. In seismic regions, airport terminals must be designed to withstand ground shaking and minimize damage during an earthquake. Geotechnical engineers use seismic site response analysis to assess how the soil behaves under dynamic loading. Foundation systems may incorporate seismic isolation technologies or deep foundations to enhance the structure's resilience to earthquake-induced forces. Groundwater control. Groundwater levels can fluctuate, especially in areas near water bodies, affecting the stability of terminal foundations. Geotechnical engineers assess the risk of uplift forces due to high groundwater pressure and implement dewatering systems, such as pumping wells or wellpoint systems, to control the groundwater and ensure a stable foundation environment. Soil structure interaction (SSI), the interaction between the soil and terminal building structure, is essential for determining the performance of the foundation and the building's response to external loads. SSI analysis is performed to ensure that the foundation adequately distributes loads to the soil and that the terminal building will perform as intended under both static and dynamic conditions. 4.2.3 Geotechnical Challenges in Airport Infrastructure. The construction of airport runways and terminals presents unique challenges for geotechnical engineers. Heavy and repetitive loading. Both runways and terminals experience heavy, repetitive loads due to the constant movement of aircraft and passengers. This requires careful consideration of pavement design, foundation stability, and soil compaction to avoid premature failure or deformation. Environmental and weather conditions. Airports are exposed to a wide range of environmental conditions, such as extreme temperatures, moisture fluctuations, and freezing. Geotechnical engineers must consider how these factors influence soil behavior, such as frost heave and soil shrinkage. They may use techniques like thermal insulation and frost-protected foundations to mitigate these effects. Soil contamination. Airports often operate in environments where there is potential for soil contamination due to chemicals, fuel spills, or de-icing agents. Geotechnical engineers must consider the long-term impacts of soil contamination on the foundation and implement necessary remediation strategies to ensure the stability and safety of the infrastructure. Airfield expansion and modification. Airport projects often involve the expansion or modification of existing runways or terminal buildings. Geotechnical engineers must assess the condition of the existing soil and foundation systems, determining whether they can accommodate the additional load or if improvement techniques such as soil stabilization or deep foundation replacement are necessary. 4.2.4 Innovations in Geotechnical Design for Airport Infrastructure. Recent advancements in geotechnical engineering are being applied to airport infrastructure projects to enhance performance, sustainability, and efficiency. Geosynthetic reinforcement. The use of geosynthetics, such as geogrids, geotextiles, and geomembranes, has been expanding in airport construction due to their ability to improve soil stabilization, reduce settlement, and enhance drainage. Geosynthetics are now commonly used to reinforce runway subgrades, enhance soil bearing capacity, and reduce the potential for cracking in pavements. Intelligent compaction and monitoring. Advances in intelligent compaction technologies enable real-time monitoring of soil compaction during construction. This technology allows for better control of the compaction process, reducing the likelihood of future settlement or deformation. Sustainable practices. Geotechnical engineers are increasingly incorporating sustainable practices into airport infrastructure design, such as using recycled materials in pavement construction, employing low-carbon cement technologies, and designing for energy efficiency in terminal buildings. These efforts contribute to minimizing the environmental impact of airport construction and operation. 4.2.5 Conclusion. Geotechnical engineering is fundamental to the design and construction of airport runways and terminals. Through comprehensive site investigations, advanced design techniques, and innovative solutions, Engineers ensure that airport infrastructure can withstand the dynamic loads and environmental challenges associated with aviation operations. By carefully considering soil behavior, foundation stability, drainage, and environmental impacts, geotechnical engineers play a vital role in creating safe, efficient, and sustainable airports that support the growing demands of air travel. Chapter 14: Geotechnical Engineering for Infrastructure Projects. 14.3 High-rise Building Foundations and Soil Considerations. The design and construction of high-rise buildings are complex tasks that require careful consideration of soil conditions, foundation systems, and the interaction between the building and the underlying ground. High-rise buildings exert substantial loads on the foundation, and the performance of the foundation directly impacts the structural integrity, safety, and long-term stability of the building. This section delves into the key geotechnical considerations involved in the foundation design of high-rise buildings and the challenges posed by different soil conditions. 14.3.1 Geotechnical Challenges for High-Rise Building Foundations. High-rise buildings, often ranging from 10 to over 100 stories, require specialized foundation solutions to support their substantial weight and ensure stability under both static and dynamic loads. The primary geotechnical challenges associated with high-rise buildings include high loads and vertical settlement. High-rise buildings exert significant vertical loads on the soil, which can lead to settlement or differential settlement. Differential settlement may result in structural damage or misalignment of building elements. It is essential to design foundations that minimize settlement, which is achieved by careful evaluation of soil strength, compressibility, and the use of appropriate foundation systems. Lateral loads. In addition to vertical loads, high-rise buildings must also withstand lateral forces from wind, seismic activity, and other environmental factors. Geotechnical engineers must ensure that the foundation provides sufficient resistance to these lateral loads, especially in areas with weak or loose soils. Soil structure interaction. SSI high-rise buildings are subject to complex soil structure interaction (EX), which can ECT the dynamic response of both the building and the foundation. The interaction between the building structure and the underlying soil must be analyzed to predict how both will respond to loads, vibrations, and movements. Groundwater conditions. Groundwater can complicate foundation design for high-rise buildings, especially if the water table is high or fluctuates seasonally. Groundwater can lead to uplift pressures, complicate construction techniques, or even cause soil erosion or weakening. The design of drainage systems and groundwater control measures is crucial for preventing water-related issues. 14.3.2 Foundation Design Options for High-Rise Buildings. Several types of foundation systems are used in the construction of high-rise buildings, each depending on the soil conditions, the building's height, and the design requirements. Geotechnical engineers carefully evaluate the soil profile and select the most appropriate foundation type, which may include the following. Shallow foundations. Shallow foundations, such as spread footings or mat foundations, are used in areas with strong, stable soils that can bear the weight of a high-rise building without excessive settlement. A mat foundation, also known as a raft foundation, is often used when the building is large or the soil is not uniform, as it spreads the load across a wide area. OMAT foundation. In cities where soil may vary greatly from one area to another, mat foundations are used to distribute loads more evenly and reduce the risk of uneven settlement. These foundations can be designed as reinforced concrete slabs that cover the entire footprint of the building, or spread footings. In some cases, individual footings or pads are used beneath columns or walls. Spread footings are effective when the soil has sufficient strength to support the building's load. Deep foundations. When the soil near the surface is weak or compressible, deep foundations are used to transfer the building's load to stronger, deeper layers of soil or bedrock. These foundations include piles and caissons, which can be driven, bored, or drilled into the ground to reach deeper, more stable layers. Piles. Piles can be made from concrete, steel, or timber, and they are driven or drilled into the ground to provide support in weak or loose soils. Piles are designed to bear the loads of the building by reaching deep into stable strata that are capable of supporting this structure. The choice of pile type, e.g., end-bearing piles, friction piles, depends on soil conditions and load requirements. Caissons. Caissons, or drilled shafts, are similar to piles but are typically larger in diameter. They are drilled into the ground to reach deeper layers of soil and bedrock. Caissons are often used when deep foundations are required in soft soils or under significant loads. Basement slab foundations. In addition to the foundation system, high-rise buildings often require a basement slab to serve as both a foundation and the base of the underground structure. These slabs are generally reinforced concrete and must withstand both vertical and lateral loads, as well as groundwater-related challenges. 14.3.3 Soil behavior and testing for high-rise foundations. The success of a foundation for a high-rise building depends on a thorough understanding of the soil's behavior under different loads. Geotechnical engineers conduct various soil tests to assess the soil's strength, compressibility, and overall behavior. Some of the most common tests include standard penetration test, SPT. This test is used to assess the soil's resistance to penetration and provide information about the soil's density and strength. It is particularly useful for determining soil stiffness and providing an estimate of the load-bearing capacity of the soil. Cone penetration test, CPT. The CPT provides continuous data about soil resistance, helping to define the soil profile more accurately. This test is used to assess the stratigraphy of the soil and to evaluate its ability to support heavy loads. Plate load test. This test is used to determine the ultimate bearing capacity of soil and its settlement characteristics. It is particularly useful for evaluating shallow foundation performance, borehole drilling, and sampling. Geotechnical engineers often take soil samples from different depths to determine the type of soil and its characteristics, such as moisture content, compaction, and shear strength. These samples are tested in the laboratory to evaluate factors such as consolidation behavior, plasticity, and grain size distribution. Shear wave velocity test. This test assesses the stiffness of the soil and is essential for determining the soil's response to dynamic loads. shear wave velocity, is particularly important in earthquake engineering and for evaluating seismic risks. 14.3.4 Advanced Geotechnical Techniques for High-Rise Foundations. In addition to traditional soil tests and foundation designs, advanced geotechnical techniques are increasingly being used to improve foundation performance for high-rise buildings. Soil improvement techniques. In areas with weak soils, soil improvement methods may be applied to enhance the bearing capacity and reduce settlement. Techniques such as grouting, vibrocompaction, and geotextile reinforcement are commonly used to stabilize and strengthen the soil, making it suitable for the heavy loads of high-rise buildings. Deep soil mixing. DSM deep soil mixing involves blending the soil with cement or other stabilizing agents to improve its strength and steadiness. This technique is used in areas where traditional foundation systems are not feasible or when the soil is prone to liquefaction. Geotechnical instrumentation and monitoring. In high-rise building projects, continuous monitoring of soil behavior, settlement, and foundation performance is essential. Instrumentation such as piezometers, inclinometers, and strain gauges is installed to track movements, moisture content, and pore pressure in the soil. Real-time data from these instruments helps engineers detect any potential issues early and take corrective action if necessary. 14.3.5 Case studies in high-rise foundation design. Several high-rise building projects around the world demonstrate the importance of geotechnical considerations in foundation design. Burj Khalifa, Dubai, UAE. The Burj Khalifa, the tallest building in the world, was built on a foundation consisting of large reinforced concrete mats and board piles. The deep piles were drilled into hard bedrock to anchor the massive structure and provide stability under wind and seismic loads. Geotechnical engineers conducted extensive soil testing to ensure that the foundation could support the building's extreme height and weight. One World Trade Center, New York, USA. The foundation of One World Trade Center involved deep drilling into glacial soils and bedrock. The design included large-diameter board piles to ensure the stability of the tower, which is located in an area with complex soil conditions due to its proximity to the waterfront. Geotechnical engineers also implemented extensive dewatering systems to manage the high groundwater levels. 14.3.6 Conclusion. The foundation design for high-rise buildings presents unique challenges due to the significant loads and complex soil conditions encountered at construction sites. Geotechnical engineers must evaluate soil behavior through advanced testing techniques, select appropriate foundation types, and implement soil improvement strategies to ensure the building's stability and safety. By understanding the interaction between the structure and the soil, engineers can design foundations that provide long-term performance, minimize settlement, and withstand dynamic forces. The continued development of innovative geotechnical technologies will further enhance the efficiency and sustainability of high-rise building projects. Chapter 14. Geotechnical Engineering for Infrastructure Projects. 14.4 Geotechnical Engineering in Dams and Reservoirs. Dams and reservoirs are critical infrastructure elements that provide water storage, flood control, and hydroelectric power generation, among other functions. The design and construction of dams and reservoirs require a comprehensive understanding of Geotechnical engineering principles as the behavior of the soil and rock beneath and around these structures plays a key role in their stability and performance. In this section, we explore the geotechnical engineering considerations that must be taken into account when designing dams and reservoirs. We will discuss various types of dams, the importance of soil and rock mechanics, foundation considerations, seepage control, and techniques for monitoring and maintenance. 4.4.1 Types of dams and their geotechnical considerations. There are several types of dams, each with unique geotechnical challenges based on the materials used, the construction method, and the environmental conditions of the site. The primary types of dams include earth-fill dams. These are constructed using natural materials such as clay, sand, and gravel. The dam is built up in layers, often with a core of impermeable material, to prevent water seepage. Geotechnical engineers must assess the stability of the materials used, the compaction of each layer, and the potential for settlement or sliding. Geotechnical considerations. Soil strength, compaction characteristics, and the ability of the dam to resist erosion are all key factors. The core must be designed to be impermeable to prevent seepage, and the outer layers must be stable under both static and dynamic loads, such as those from earthquakes. Concrete gravity dams. These dams rely on the mass of concrete to resist the water pressure and are typically constructed in narrow valleys. The foundation must be strong enough to support the immense weight of the concrete structure. Geotechnical considerations. The foundation of a gravity dam must be carefully evaluated to ensure that it is capable of supporting the structure without excessive settlement. A concrete gravity dam requires the soil or rock beneath it to have high shear strength to resist sliding forces. Engineers must also evaluate the potential for cracking due to thermal expansion and contraction of the concrete. Arch dams. Arch dams are curved structures that transfer water pressure to the canyon walls. These dams are typically used in narrow gorges where the surrounding rock can support the forces exerted by the water. Geotechnical considerations. For arch dams, the rock quality and stability at the site are critical. The rock must be strong and resistant to cracking under pressure, and the dam's design must account for rock mass heterogeneity. Site investigations and rock mechanics analyses are crucial for ensuring the foundation's integrity. Rockfill dams. These dams consist of large rocks placed over a compacted earth core. The core prevents water seepage, while the rockfill provides structural support. Rockfill dams are typically constructed in regions with abundant rock resources. Geotechnical considerations. Similar to earth-fill dams, the materials used for the rockfill must be stable and resistant to erosion. The design must ensure that the rockfill is compacted adequately to minimize settlement and maintain stability over time. Geotechnical engineers also focus on the internal drainage of the dam to ensure it remains free from water accumulation that could cause instability. 4.4.2 Foundation design and site selection. The foundation of a dam is critical to its stability. The site selection process, along with a thorough geotechnical investigation, is crucial in ensuring that the foundation can support the dam's weight and resist the forces exerted by water pressure. Key considerations for foundation design and site selection include site investigation. Detailed geotechnical investigations are necessary to characterize the soil and rock properties at the dam site. These investigations may include soil borings, laboratory testing, rock core sampling, and geophysical surveys. The purpose of these tests is to evaluate the strength, compressibility, and permeability of the foundation materials. Foundation stability. The foundation must be able to resist sliding, settlement, and overturning forces. For concrete dams, engineers assess the shear strength of the rock or soil beneath the dam and design the foundation to distribute the weight evenly. For earthfill and rockfill dams, stability analysis is crucial to prevent failure due to slumping or excessive settlement. Seismic considerations. Seismic activity can have a significant impact on dam stability. Geotechnical engineers assess the potential for seismic loading at the dam site and design the foundation to resist seismic forces. This may involve incorporating additional reinforcing elements, such as shear keys or flexible joints, to allow for movement during an earthquake. Groundwater and seepage control. Groundwater conditions play a crucial role in dam foundation design. High groundwater levels or seepage through the foundation can undermine the stability of the dam. Engineers must assess the hydrogeology of the site to determine the potential for seepage and design appropriate drainage and QO systems, such as QO walls or impervious layers, to minimize the flow of water through the dam's foundation. 14.4.3 Seepage control and drainage systems. Seepage through a dam can be a major cause of failure if not properly controlled. Water seeping through the dam can erode the soil or rock foundation, weakening the structure and potentially leading to catastrophic failure. Several methods are used to control seepage and drainage. QO walls. A QO wall is an impermeable barrier, usually made of concrete or a mixture of soil and cement, which is placed deep in the foundation to prevent water from passing through. QO walls are especially important for earthfill dams, where seepage through the core or foundation could compromise the structure's stability. Toe drains and filter systems. Toe drains are used to remove water that may accumulate at the base of the dam. These systems typically consist of perforated pipes or gravel-filled trenches that allow water to flow out of the dam while preventing the movement of soil particles. Filters are often used in conjunction with drains to ensure that fine materials do not clog the drainage system. Blanket drains. Blanket drains are placed beneath the dam structure to provide a continuous drainage system. These drains are typically composed of gravel or coarse sand, which allows water to pass through without eroding the underlying soil. Blanket drains are particularly useful for preventing water buildup beneath the dam, which could cause uplift pressures and instability. Seepage monitoring. Ongoing monitoring of seepage is critical for detecting potential issues before they become serious. Engineers use instruments such as piezometers and seepage meters to measure pore water pressure and flow rates in the foundation. This data is used to assess the effectiveness of seepage control systems and to ensure the long-term safety of the dam. 14.4.4 Monitoring and maintenance of dams and reservoirs. Geotechnical engineers play a vital role in the ongoing monitoring and maintenance of dams and reservoirs. Regular inspection and testing are necessary to ensure the continued stability of the dam and to detect early signs of potential failure. Monitoring includes piezometers. These instruments measure the water pressure within the soil or rock beneath the dam, providing valuable data about changes in the groundwater conditions and potential seepage. Inclinometers and tiltmeters. These instruments measure the movement of the dam and foundation, allowing engineers to detect any settlement or tilting that could indicate instability. Seismic monitoring. Seismic sensors are installed to measure ground motion during earthquakes and assess the impact of seismic events on dam stability. Visual inspections. Engineers conduct regular visual inspections to check for signs of cracking, erosion, or other damage to the dam structure. 4.4.5 Case studies in dam engineering. Several large-scale dam projects around the world demonstrate the importance of geotechnical engineering in ensuring the stability and safety of dams. Three Gorges Dam, China. The Three Gorges Dam, one of the largest hydroelectric dams in the world, required extensive geotechnical studies to evaluate the foundation conditions in the Yangtze River Valley. The foundation was designed to resist significant seismic forces, and seepage control systems were implemented to ensure the dam's long-term stability. Hoover Dam, USA. The Hoover Dam, located on the Colorado River, was built on a foundation of hard limestone and granite. Geotechnical engineers carefully assessed the rock mass conditions to ensure that the dam would remain stable under the immense water pressure. The dam's design incorporated a complex drainage system to control seepage and prevent water from weakening the foundation. 4.4.6 Conclusion. Geotechnical engineering is a fundamental component of dam and reservoir design. The selection of foundation types, assessment of soil and rock behavior, and the implementation of effective seepage control measures are critical to ensuring the safety and longevity of these structures. By utilizing advanced geotechnical techniques and conducting thorough site investigations, engineers can design and maintain dams that provide reliable water storage, flood control, and energy generation while minimizing risks to the surrounding environment and communities. Chapter 14. Geotechnical Engineering for Infrastructure Projects. 14.5 Case Studies of Large Infrastructure Projects. In this section, we explore several case studies of large infrastructure projects where geotechnical engineering played a crucial role in ensuring successful design, construction, and performance. These case studies highlight the complexities, challenges, and innovations in geotechnical practices used to address specific site conditions and engineering requirements. 4.5.1 The Channel Tunnel, UK and France. The Channel Tunnel, also known as the Channel, is a 50.5 kilometers, 31.3 miles undersea tunnel linking Folkestone in the UK and Coquelles near Calais in France. It is one of the most ambitious civil engineering projects of the 20th century and represents a monumental achievement in geotechnical engineering. Geotechnical challenges. The tunnel traverses a variety of geological formations, including soft clays, limestone, chalk, and gravel. The presence of groundwater, combined with the challenging geology of the region, pose significant risks during the construction process. Engineering solutions. Extensive geotechnical investigations were carried out prior to construction, including borehole sampling and seismic profiling to assess the soil and rock conditions. A combination of tunneling methods was used, including the tunnel boring machine (TBM) and the cut and cover method, to manage the errant ground conditions encountered along the tunnel route. Geotechnical innovations. The design and construction incorporated advanced techniques such as ground freezing to temporarily stabilize soft ground and prevent groundwater inflow during tunneling operations. Additionally, the use of precast concrete tunnel segments allowed for rapid construction and ensured structural integrity in a highly variable geological environment. Outcome. Despite challenges, the Channel Tunnel was completed in 1994, offering a seamless link between the UK and mainland Europe. The project highlighted the importance of advanced site investigation techniques, ground stabilization methods, and tunnel design innovations in overcoming complex geotechnical challenges. 4.5.2 Burj Khalifa, Dubai, UAE. The Burj Khalifa, currently the tallest building in the world, stands at 828 meters, 2,717 feet tall. Located in Dubai, UAE, this skyscraper required cutting-edge geotechnical engineering to ensure stability in the highly variable desert soils and to support the immense weight of the structure. Geotechnical challenges. The site of the Burj Khalifa is located on soft, sandy soil, overlying a layer of limestone. The weight of the tower and the seismic activity of the region required a solid foundation system to ensure the building would remain stable under both static and dynamic loads. Engineering solutions. The foundation system for the Burj Khalifa was designed as a large mat foundation supported by board piles. The piles penetrate through the soft sand layer to reach the stronger limestone bedrock below. Extensive site investigations, including deep boreholes and geophysical surveys, were conducted to understand the soil conditions in great detail. Geotechnical innovations. The design incorporated high-strength reinforced concrete and post-tensioning techniques to manage the forces acting on the building. A significant challenge was the large volume of concrete required for the foundation, which needed to be poured in a continuous operation to avoid thermal cracking. Specialized cooling systems were also used to manage the temperature of the concrete as it cured. Outcome. Completed in 2010, the Burj Khalifa has set a benchmark for the tallest buildings in the world. The success of its geotechnical design demonstrates the importance of advanced soil testing, deep foundation techniques, and careful monitoring during construction to ensure the structural stability of skyscrapers in challenging environments. 4.5.3 Tokyo Bay Aqua Line, Japan. The Tokyo Bay Aqua Line is a 15.1 kilometers, 9.4 miles, expressway and tunnel system that connects Kawasaki, Kanagawa, and Kisarazu, Chiba, under Tokyo Bay. It includes a tunnel section under the bay and an elevated bridge section. This project required significant geotechnical engineering to address the complex underground and marine soil conditions. Geotechnical challenges. The tunnel segment of the project passes through deep marine sediments under Tokyo Bay. These soft, saturated soils presented major challenges in terms of excavation, groundwater control, and stability. Additionally, the tunnel had to be constructed in close proximity to active seismic zones. Engineering solutions. The project utilized shield tunneling machines (STM) to excavate through the soft marine soils, minimizing ground disturbance and controlling groundwater inflow. Geotechnical engineers also employ deep soil mixing techniques to stabilize the soft clay layers before tunnel construction. A combination of precast concrete tunnel segments was used for efficient construction and safety. Geotechnical innovations. To address the challenges posed by the underwater soils, a continuous dewatering system was implemented to manage groundwater inflows during construction. Furthermore, the tunnel's alignment was optimized to avoid areas of known geohazards, such as fault lines, and to minimize the impact of seismic activity on the tunnel structure. Outcome: the Tokyo Bay Aqualine opened in 1997, providing a crucial transportation link between the two regions and significantly reducing travel time. The project showcases the importance of managing complex marine soil conditions and groundwater control during large-scale infrastructure projects. 14.5 point for the Panama Canal expansion. The Panama Canal expansion project, also known as the Third Set of Locks project, involved the construction of a new set of locks and the widening and deepening of the canal to accommodate larger vessels. This project required extensive geotechnical engineering due to the challenging site conditions and the scale of the project. Geotechnical challenges. The region surrounding the Panama Canal is characterized by highly varied soil conditions, including clay, silt, and volcanic rock. The canal's proximity to active fault lines and the need for a stable foundation under the new locks created additional complexities. Engineering solutions. Extensive geotechnical investigations, including soil sampling, borehole testing, and seismic hazard assessments, were carried out to evaluate the soil and rock properties. The foundation for the new locks was designed using gravel-filled embankments and reinforced concrete structures to provide stability in the highly variable and seismic-prone soil conditions. Geotechnical innovations. One of the key innovations was the use of deep soil mixing techniques to improve the strength and stability of the soil at the base of the locks. This process involved mixing cement and other stabilizing agents into the soil to create a stronger, more durable foundation for the locks. Outcome: the Panama Canal expansion, completed in 2016, significantly increased the canal's capacity and allowed it to accommodate the next generation of large vessels, known as Panamax ships. The success of the geotechnical engineering in this project ensured the stability of the locks and surrounding structures while minimizing risks associated with seismic activity and soil variability. 14.5.5 London Crossrail Project UK. The London Crossrail project, now known as the Elizabeth Line, is a major railway infrastructure project that involved the construction of a 118-kilometer, 73-mile railway. Thank you for your attention in watching this video lecture on the Triune Biblical University Global Extension USA channel. Kindly like, share, subscribe, and comment to help us bring more educational content your way. The link to the next part of this video will be posted in the description section.